So, good morning everyone, and welcome to this talk where we will go out and meet the social side of our code. And the reason I wanted to talk about this was that I'm well aware that we in the industry, we know about the importance of teamwork. And we know about the power of team autonomy. And yet, I've seen in practice, it's incredibly hard to get those things right. And worse, when we fail, we tend to fail miserably. So in this talk, I'd like to approach software development from a different angle. I like to approach it from the people side, from the side of social psychology. And you might ask yourself, why do I feel qualified to talk about this? So it's a fair question, and let's start with my technical background. Because I've been a software developer for 21 years now, I've written a lot of code, and I had an engineering degree to start with. But my background is also a little bit different, because I also have a degree in psychology. I spent 6 years at the university, and it's one of my big interests. So what I try to do these days is to take my psychological perspective and put it on top of my technical background. And I've written 2 books about that topic, and that's also the topic that we're going to explore today. So when I tell people that story, that I went into psychology to better understand how we develop software, the single most question I get is this: why? Why is it so hard to write good code? And I find that fascinating because it is a good question, but it's also the wrong question. Because I have to tell you, the more I learned about psychology, the more surprised I became that we're capable of writing any code at all. It just shouldn't be possible. Software should be way too hard to us, and yet we do it every single day. And sometimes our code even works. And the reason we managed to pull this off is because the human brain has evolved a lot of interesting shortcuts and workarounds that let us take a high-level understanding of all that complexity we have in our code and squeeze enough of that understanding into our head so that we can reason about it efficiently and modify it to have it behave the way we want to. However, this tendency towards shortcuts and workarounds might serve us less well in a social setting. And the result of that might be what we refer to as social biases. And social biases might be disastrous to a software project. And yet, social biases are there for a reason. They are there because they do appear to simplify decision-making in complex situations. And social situations are incredibly complex. So I like to elaborate a little bit about that by taking you through a controversy. So within psychology, we have a very good instrument to measure personalities. It's something called the Big Five. And the basic idea is that you have 5 different dimensions of personality. So things like extraversion, openness to new experiences, neuroticism, and so on. And each one of you is a complex combination of your scores on these 5 different dimensions. Now, the question is, if I knew the personality score of each one of you, could I predict how you will act and behave in a certain situation? One group of psychologists claim that, yes, of course, that's what a personality is, right? And then we had the other group of psychologists that claimed that, no. It doesn't matter what kind of personality you have. The situation is much more powerful. And the first time I read about this, I was like, hey, I've seen this before. This is dynamic versus static typing, right? This is Git versus Mercurial, Emacs versus Vim. So it's almost like this tendency towards controversy and strong opinions is a human thing. Who knew? But like most strong controversies, it turned out that the truth was somewhere in the middle. And I'd like to read a quote for you because this is something that surprised me a lot when I learned about this. This is a quote from a psychologist called Michel. And Michel states in his research that 91% of the differences in your behavior in a particular situation cannot be measured by personality tests. So it turned out that personality is indeed an important factor. It predisposes you towards a behavior, but it doesn't determine that because the situational forces are so incredibly powerful. And in a way, these are good news, because it's incredibly hard, perhaps even impossible, to change one's personality. But the situation, that's something we can work with, right? We can modify the situation to kind of stimulate the behavior we would like to see. And this is interesting to us as software people. And so I like to take you on a metaphor, because I came to view software systems as a combination. So I like to view software systems as having both a personality and situational forces around them. So to me, a system's personality, that's its code, its architecture. And those parts are important, because just like a people personality, a system's code, its architecture, it predisposes what we can do with the system. Some features are going to be easy to implement, others are going to be hard. But I find that the other side of this equation is even more important. Because the way we, as the people who have working on it, the way they're organized, the organizational patterns they are used, determines the outcome of any software endeavor. And get that right, and you can succeed no matter what the code base looks like. It might not be optimal, but you will succeed. And if we get that wrong, it doesn't matter how clean our architecture is or how nice our code looks. The outcome won't serve anyone well. And these situational forces are incredibly strong on a software project, and we might not always be aware of it. And I would like to give you an example by telling you a story about something that happened to me maybe a decade ago. So at that time, there was this company. They were going to do a new generation of an existing product. And they had very good historic data that showed them that this is going to take you 1 year. Using your 5 in-house developers, it's going to take you 1 year. And yeah, I know exactly what all of you think right now. Software project, that's predictable. Crazy. And of course, pretty soon someone came up that, yeah, I mean, 1 year, I'd like to have this in 3 months. Can I have this in 3 months? How do you do that? How do you take something you know it's going to take 1 year and you compress it down to just 3 months? It's easy. It's basic math. You just throw 4 times as many developers on it. And they did. And I wasn't part of the original project. I came in later for, how should we put it, the post-mortem. Because this project didn't finish in 3 months. In fact, it didn't finish in 1 year either. And I was part of like a task force trying to bring it back on track. And one of the things I did was that I interviewed and talked to the people who worked on the project. And they told me a lot of interesting things. The first thing that everyone agreed upon and complained about was that they had so many defects. They had like a mountain of defects. And this wasn't surprising to me, given what we know about the relationship between overstaffed projects and a negative quality. And this is something I'm going to come back to later. But the second thing people told me really surprised me. Because a lot of the developers claimed that the code was really, really hard to understand. And this was surprising to me because prior to those interviews, I had actually reviewed a significant portion of the source code. And let's be fair here, it wasn't exactly a work of art, but it wasn't bad either. It was actually good enough, and it was definitely not hard to understand. So I was surprised about this, until I realized the reason this happens is because even if you write a piece of code yourself today, 3 days later, it's looked completely different because 5 other developers have been working on it in the meantime. More precisely, this makes it impossible to build up stable mental models of what the source code actually looks like. So that means you take away all those opportunities your brain has to use its shortcuts and workarounds to take that complexity and stuff it into your head. And the outcome of this project shouldn't come as a surprise to anyone who has read the Mythical Man Month. The Mythical Man Month is perhaps best known for what we now call Brooks' Law, that adding manpower to late project makes it even later. And the reason for this, Fred Brooks claims, is that with each additional person you staff onto a project, you get a fixed number of hours available. And those hours will increase linearly with each additional person. However, the possible coordination paths will increase almost at an exponential rate. So that means at some point in this curve, we reach a tipping point where each additional person we stuff onto it, those extra hours get consumed by the additional coordination needs, and then some. But I would like to claim that there are more dangers with overstaffed project than just Brooks' Law. Because what we also run into are motivational factors. And in particular, there's one motivation loss called social loafing. So how many of you have heard about social loafing? Ah, cool, I got something new for you. That's great. So social loafing is a type of motivation loss that occurs when we feel that the success of our team depends very little on our own actual efforts. So what we do in that situation is that we pretend to do our part of the work, but in reality, we really just try to look busy and hope that someone else will keep up the efforts instead. It's a very human thing and a very real thing. And the reason this happens is that when the goals of a particular project aren't clearly communicated, or if we enforce arbitrary deadlines upon a project. And I have found that the larger a software project is, the harder it becomes to make sure that everyone has those shared goals. It becomes much harder to see how my small contributions fit into the larger picture. And I think there's a reason for this. I think there's a reason we keep overstaffed projects. And I'd like to demonstrate that to you by giving you a small challenge. So please have a look at the following piece of code. Who can tell me if this code is a coordination bottleneck for our 5 feature teams? No, of course, you cannot, because you don't have the context, right? And I find it fascinating. If we look at just the code, we cannot tell, is this code developed and maintained by a single developer, or is this a major coordination bottleneck for the whole organization? And this is something I like to refer to as the tragedy of software design, that the organization that builds the code is invisible in the software itself. And the consequence of this is that we start to treat symptoms instead of the real issues. So, to make sure we actually address the things that really, really matter and get rid of the symptoms in the process, we need to take a different view of code. We need to add the organization, we need to add the people and make them visible in our software. How can we do something like this? Well, one starting point is to measure something I call inter-team coordination needs in code. And here's how it works. Basically, I consider each subsystem, each module that we have as a box. And then I look at who has actually written that code. And the more a particular team has contributed, the larger their area of the box. So in this case, we see that team 1 have contributed like 51% of the code, team 2, 23%. And I can also see how diffused the efforts are, how distributed they are across different teams. Now, to work with this on scale, we need to turn this into a quantitative metric. And one way of doing that is by calculating something called a fractal value. Now, you don't really need to look that much at the math. I don't want to do this to you this early in the morning. But I put it here for reference, and in case you want to read more, there's a great research paper on it about fractal values. All you need to understand from this formula is that what it does is that it takes a fractal figure like this and normalizes it to the range 0 to 1. And 0 basically means that this is a modular component that a single team worked on. And the closer to 1 we get, the more different teams we have worked on this piece of code and the more diffused their efforts. Now that we have a way of measuring inter-team coordination needs, we need to get the raw data. How can I find out where the different teams actually work over time? And those of you who know me or have seen my presentations before, you know that I'm a big fan of version control data. Guess we all have our odd hobbies, right? So the reason I enjoy version control data is because version control data is actually social data. Our version control system knows exactly which developer that worked on which piece of code. And version control data also contains a lot of interesting patterns that we cannot see in the code itself. So one example on that is that, for example, files that tend to change together as part of the same commits over and over again, that's something we look into later today. I find that the main limitation with version control data is that it's obviously centered around individuals. But the interesting unit of measure in an organization is the team. So what I do with version control is that I tend to put some scripting on top of it, where I just map the individuals to teams. And then I can do my calculations on that level. Another limitation of version control data is that it's centered on files. But again, when we talk software architectures, the interesting unit of measure is architectural building blocks, logical components. So what I do with version control data is that I typically map a group of files. Perhaps our architecture is expressed in the directory structure. So I map directories to logical components. And again, you can basically use any grouping, any mapping that you want, as long as those resulting components carry a meaning in your architectural context. We're going to look at some tooling options later, but with that covered, we have all the tools we need to investigate some social ways of failing with software architecture. So I like to show you a number of patterns here. Let's have a look at the first one. Who recognizes this pattern? Yeah, most of you, cool. Yeah, this is a true classic, right? Model view controller. And if you hear that someone has a model view controller pattern, I promise you this, if you look at the code, this is never ever what a model view controller looks like, right? Because we know it's not enough. We will need a bunch of other layers, right? The services layer for application logic, we need repositories and whatnot. And of course, this is not enough either, because we all know that we need a data abstraction layer as well. And the reason we need a data abstraction layer is something I've talked about a lot. I still haven't really come up with a good answer. Most of the practical use cases I've seen seem to refer to giving our mock frameworks enough exercise or something. It's good to keep them healthy. Now, that's of course not where it stops, because typically you will find that you have a business layer, you have new models, you have view helpers and so on. So 10 to 11 layers are actually quite common. Now, let's pretend we have this kind of architecture. And let's say we want to add a new feature to it. We want to add something that's visible to the end user. What will our change patterns look like? Well, something like this. And in fact, in the studies I've done, I've seen that somewhere between 30 to 70% of all commits will ripple through the entire software stack. And the lower number here, that refers to systems that are more in a stable maintenance phase. So most of the changes we do are bug fixes, which tend to be local. And the higher number is for systems that are under active development. So to me, this sounds quite expensive, right? 70% of our changes, and we need to revisit 10, 11 layers. And I think the main reason for that is because this is the building blocks in a layered architecture are technical building blocks. So these are basically optimized for replacing a technical responsibility. And that happens, but it's a rare case. And that trade-off we do here is at the expense of the changes we do to that system every single day, which tends to be feature-driven, which tends to be use case-oriented, and there's a huge conflict between those two sides. And the consequence of that is obvious when we start to add the organizational side, because what happens if we stuff multiple feature teams onto an architecture like this? Well, let's have a look at it, and this is real data from a real system. I just made it anonymous to protect the guilty. So, the visualization here, the way you read it, is that each circle represents a subsystem, a logical component, and the size of the circle just represents the amount of code. So the larger the circle, the more code you have in that subsystem. And that's not the important aspect. The important aspect is the color, because the color reflects our fractal value. That is, how many teams do we have on that part, and how diffused are their efforts. And we see here, if we have multiple teams working on this, what will happen is that you have a constant congestion in each part of the software architecture, because all teams will work in all parts of the code all the time, but for different reasons, since they work on different features. Now, this situation leads to one of the most common questions I get. Should we use component teams or feature teams? We kind of tried both and none of them really worked. And again, I find it an interesting question, but I don't think that question can be answered in isolation without also considering the personality side of our system, its architecture. And for layers, both of those choices have their trade-offs. So with component teams, what tends to happen is that if each kind of component team owns a layer there, what's going to happen is that you get pretty long lead times because there's going to be a lot of handover, a lot of focus around API changes and stuff like that. But then you switch to feature teams, and what happens is that your whole code base turns into a coordination bottleneck. So none of them are perfect, and that said, I have seen component teams work with layered architectures at scale and actually get things done. I'm yet to see a single example of a feature-oriented organization that manages to pull this off. There might be such a thing out there, but I haven't seen it yet. So we're going to come back to layered architectures and monoliths. But before that, I'd like to take a small excursion, a small detour into the world of microservices. Because microservices are supposed to solve this for us, aren't they? So some of the most common arguments I hear, the most common motivations I hear for microservice architectures are that we want to keep our system, our components, our services loosely coupled. Because if those are loosely coupled, we can get team autonomy. That's a good thing, right? Minimize our coordination needs. And as a consequence, we can also start to deploy our services independently and scale them independently. That's absolutely great. So let's look at a typical microservice architecture. And this is an architectural style, this particular example, that I've seen multiple times over the past year. So this is not a fluke either. Let's have a look at it from the people side, from the side of inter-team coordination needs. This is what it looks like. Wow, looks exactly like that layered monolith. How could that be? Well, we see here we have 3 to 4 teams working on each one of those services. Now, the hint to this outcome, to this behavior, is in the names of the services. If we look at them, we see that they have names like a translation server, like an access control server, like a diagnostic server. Again, these are technical building blocks. So what we have here is not so much a microservice architecture, as it's more like distributed layers, right? So the reason we get low team autonomy in this case is because the architecture is, again, technically oriented. But the work that your teams do, the work that your feature teams do, it's end-user driven. It's driven by feature requests that ripple through the entire service stack. So by having a quick look at that, we see that no, they are not really loosely coupled, and I'm going to show you soon how we can actually measure that. And as a consequence, we don't really get any team autonomy, because when we need to add something interesting to that system, we need to modify multiple services. So we didn't really reach our goal here. In particular, we had a failure due to lack of modularity, right? We had those huge technical building blocks. So maybe small and modular services will solve that problem. And I'm going to explain more about that, but first I need to talk a little bit about accidental complexity, because there's a strong link to modularity there. Now, with accidental complexity, I'm just referring to parts of the solution, parts of a code that are more complex than what the problem calls for. And I've found that accidental complexity tends to come in 2 major shapes. The first shape is when we have complex parts, like a complex component, a complex layer, complex subsystems. And this is the kind of accidental complexity that microservices do tend to resolve, because microservices take those large complex building blocks and break them up into smaller pieces, which puts us at risk for the second kind of accidental complexity. And that is when you look at each service in isolation, you pick up the code, and it's fairly easy to understand what it does. However, the emerging system behavior is anything but simple. And in a microservice architecture, complex interdependencies are even worse, because they tend to be invisible in the code itself. Because the different services are decoupled via networks, they are distributed, you have protocols, APIs, and service buses, and whatnot. So you cannot really see those interconnections in code. So how can we uncover them? one of the best techniques I know for this is something I call change coupling. So change coupling is fascinating in that it's invisible in the code itself. Look at the code and you cannot see it. So change coupling is something that's calculated from the evolution of your code, from your version control data. And here's how it works. Let's say we have this simple system with 3 different services. The first time we do a change to that system, we modify the subscription service and the sign-up service together. The second time, we modify a different service. And the third time, we're back to modifying the subscription service and the sign-up service together again. So if we note that this pattern continues, we can conclude that there has to be some kind of relationship between the sign-up service and the subscription service because they keep changing together over time. So this is something we can use to uncover the implicit change paths in a system. And I just want to point out that when I talk about the change here, it could be either if you have all your code, all your services in a single repository, you can basically calculate this just by looking at the things that change as part of the same commit. If you have a multi-repository code base, it's still possible, but what I use in that case is that I look for things that tend to be changed as part of the same tickets or task IDs. Now, armed with a change coupling analysis, we can start to look at microservices and reason about the cost of change. So I want to show you, again, it's some real data from real applications. And this was a streaming application. And what this visualization shows you is basically the change coupling between the services. So each one of those labels is a service, and the lines that connect them show the change coupled services. And what we see here is that there's one service called estimated conversions. And when we change that one, we have a predictable change in 7 other services. Wow, that sounds expensive. And just to show you that this isn't a fluke, there's another service here called estimated profit. Change that one, and you have a predictable change in 5 other services. Now, what happens if we put the team dimension into this? Well, the resulting inter-team coordination needs in the code looked pretty much like this. And this is fascinating because what we can see here, I don't have any scales here, but you can see that most of the services, they are pretty small circles. And in reality, though each one of the services was just like 1,000, 2,000 lines of code, tiny pieces of code that were easy to understand. And yet, what happens here is that we have 4 or 5 different teams working the same parts of the code all the time, and again, for different reasons. So why did this happen? Well, again, the hint might be in the name of those services. So we have one service here that's called subscription costs. And that sounds like a great name for an object. But perhaps it doesn't really make up a good service boundary. And then I have 2 personal favorites up here, payment accepted and payment received. Again, that sounds more like a state or an event rather than a service boundary. So I will claim what we have here, even though it's highly modular, it's more of distributed objects than services. And really, the only way to operate on an architecture like that is via shotgun surgery. You tweak one service, you have a predictable change in 10 others, and half of your test cases will fail. So we didn't really get any loose coupling here because everything is implicitly tied together. And we didn't get any team autonomy either as a consequence of that, right? And what's even worse is that we cannot really fix this by enforcing ownership. If we enforce the ownership of a service to a particular team, what will happen is that, again, you get incredible lead times. It's because still, to implement a feature, you might have 7, 8 different teams that need to synchronize their work. So it's that kind of architecture that will magically transform your weekly calendar into a chessboard of sync and planning meetings. So far, one could argue that none of those examples I've showed you are real microservices. And you would be right. But that's not the point. The point is that microservices are incredibly hard to get right. And when we design an architecture, we're also doing social design. And if we forget that, then all is lost. So please, align your architecture and your organization. Your system's personality is really going to thank you for it. And I'm going to come back to this and show you some examples on how we can pull this off. But before we do that, maybe you would like to know what kind of tools I use to do this analysis. So most of the data comes from Git. And I find it really, really fascinating that we can get pretty far by just using a Git client. So here's an example on how we can calculate the fragmentation of a particular component located in a specific directory. And in my latest book, in Software Design X-Rays, I use Git for all the case studies. So you can do a lot of stuff with just a Git client. However, at some level, you might want to have some scripting on top of it, some kind of tooling. So one possible starting point is a program called CodeMat. So CodeMat is an open source tool. It's something I wrote to accompany my previous book. It's entirely free as in beer. And it's available on my GitHub, and I still maintain it every now and then. What I also work on right now is something called CodeScene. So CodeScene is a way to automate all of these analyses, including the visualizations. And CodeScene is available for free for open source projects. So if you find these analyses useful, please consider to support CodeScene. This whole tooling field is still pretty young. So it's interesting to note that there are some really, really good tools in the academic space as well. And one of my personal favorites is this one, Evolution Radar, which is particularly strong on change coupling on a file level. So check that out if you're into that stuff. With the tools covered, let's return to where we left off, where we talked about aligning architectures and organizations, because that's like the essence of Conway's law. And Conway's law, when we apply that one, will impact the modularity of our code bases. But as we have seen so far, modularity alone doesn't guarantee a successful software architecture that will facilitate parallel work. So what I've seen works well in practice is that the modular boundaries we choose, rather than orienting them around things from the solution domain, things like technical aspects, we should take our focus from the problem domain. Because once we manage to map the problem domain to our software architecture, we typically manage to create natural team boundaries that facilitate parallel work. And I'd like to show you some examples on that. Can we pull this off in a microservice architecture? Yes, of course. People do that all the time. But as we have seen, microservices alone is not a guarantee. In particular, microservices won't cure our dependency blues. And those successful microservice architectures that I've come across, what they all had in common was that the services, their boundaries, were oriented around business capabilities. And I also recommend you, if you do microservices, that try to assign a team to each microservice, but do try to keep the teams really, really small. I usually recommend 2 to 4 people in each team. And the reason I like to keep them that small is, again, it's a social reason, because with so few people, the coordination overhead is very, very low. And in addition, in a small team, you avoid a lot of those social fallacies, like you remember social loafing, right, and motivation losses. That's something that's much less likely to happen in a small team, because it's so much easier to see how our contributions make a difference to the whole. Now, I really wish I could give you a much more specific recommendation than to say that you need to build your service around business capabilities, but I cannot. And the reason I cannot is because there's no easy fix for this. What it really comes down to is a deep understanding of the domain that we work in. We really need to be domain experts in order to pull this off. And with domain expertise, we also open up the secret to modular monolithic applications. So I'd like to go back and show you an alternative to layered architectures. This is a pattern, an architectural pattern called package by component. Has anyone ever seen a system like that? Ah, some of you, cool. There's a very good write-up by Simon Brown here that I recommend that you check out. And the basic idea with package by component is that you slice your architecture according to the problem domain. So you identify your business capabilities and express them as components. And if you manage to do that, you can basically assign a team to each one of those components and have them work in parallel. However, there's a common danger with package by component architectures. You can still run into change coupling between different components, which results in low team autonomy. How can that happen? It can happen through the database. Because I frequently see in databases turn into this, this black hole of maintenance efforts and change coupling. And it's possible to avoid it. I work on a package by component architecture myself right now. And it's always a trade-off. I think you're a bit like me in the sense that we like to use the best tool for the job. And databases, they're really, really good at things like sorting and searching. But if values like team autonomy and loose coupling are more important to us, we might have to take some of those responsibilities from a database and pull them up to application code. We might even find that we have to duplicate some data in order to keep the components independent. As a nice side effect of package by component, we also get some freedom in the details. Because with package by component, we have consistency on our architectural level, but the individual components can be implemented using different patterns. So for example, if you look at the code from CodeSyn, you will see that it's a package by component architecture, and some of those components, they might even have layers because they're a bit more complex and could benefit from that structure. Other features, other capabilities are so simple to implement that they might not even need a database, so we can pull that off in a single file. And I found that this freedom in details is a huge advantage that makes it so much easier to fit the design to what the problem really calls for. And this is a big contrast compared to layered architecture, where you enforce the same kind of style upon every single feature, no matter how complex or simple they are. So package by component is one possible alternative that can give you natural team boundaries. And this is like it's like the essence of Conway's law, right? When applied to software. But when I talk about Conway's law, I also have to mention that Conway's law, in a sense, is an oversimplification. And it's an oversimplification because if we, as in the software industry, take Conway's law and we take it to the extreme and isolate the teams too well, we might run into other problems. And those problems are social in their nature. More specifically, we might run into something called a fundamental attribution error. And the fundamental attribution error, that's when we attribute the same observable behavior to different factors depending on if it concerns our group or your group. More specifically, we tend to overestimate personality factors when explaining the actions of others. This is interesting. Remember, I told you earlier that personality only explains a small part of the behavior. So, to give you an example, let's say that your team breaks the nightly build. I know, it's a highly hypothetical scenario, but please play along with me, right? So, when that happens, because you were under tremendous amount of stress, because you tried to meet this virtually impossible deadline, and the feature was really, really hard, and the code was complex, and you were all overworked, and besides, that nightly build has never been that stable anyway. So a lot of situational factors. But you also know that when my team breaks the nightly build, it's because we are a bunch of lazy, careless cowboy hackers. So that's our personality. And I like to visualize things, and I think the best visualization I came up with for the fundamental attribution error is this one. So the fundamental attribution error can have a disastrous effect on any software organization. So what we need to do here is that we do value team autonomy, right? So we need to keep the teams independent, but at the same time, we have to bring them together. And this sounds like a contradiction, but it's only a contradiction because we fail to distinguish between operational boundaries and knowledge boundaries. And what I mean by that is that our operational boundaries, those are the parts of the team where parts of the code where we as a team do most of our work. Those are the parts where we are responsible. And those operational boundaries should be kept narrow so that we can have small teams. But the knowledge boundaries, the parts of the system that we are familiar with, the teams that we know as persons, should be much, much more broad. And the things I've seen in practice that makes this work is that, first of all, what works really well is when you start to invite people from other teams to your code reviews. Because if you do that, not only might you get a valuable perspective and input from them, you also start to learn to know them as individuals, which minimizes the risk for the fundamental attribution error. Another thing that works well is when you encourage people to rotate teams. I wouldn't enforce it, but if someone wants to work on a different team, it's likely that your whole organization will benefit from that. Finally, I've seen this work at scale when companies adopt an open source inspired ownership model. So we as a team, we own a piece of code, but anyone can make changes to it. And if they do it well enough, we'll accept the pull request. So to wrap this up, what I wanted to tell you today is that I don't think there is such a thing as a good or a bad architecture in isolation. To me, an architecture is good when it supports the changes we want to do to the system and when it fits our context. And an architecture never ever exists in a technical vacuum. Because as we have seen, the social side of your code will impact most of the important things like feature implementation efficiency, inter-team coordination. It will affect your lead times, and it will also constrain the kind of refactorings you can do to the system. So as I hope to show you today, we can actually measure the social side of code. And it's an aspect of software development that should affect most of our high-level design choices. So use it to your advantage. And if you want to read more, I want to leave you with a number of references here. I have a new book around it, Software Design X-Rays, that dives into all of these topics. And I regularly blog about it at empire.com. So I'm going to hang around for the rest of the day, and I would love to talk more about this, so please just come forward or catch me later. And now I'd like to take this opportunity and say thanks a lot for showing up, and thanks a lot for listening to me, and may the code be with you. Thanks.